Hello everyone, let me introduce myself. I am Facundo Carballo, and today I will explain you synchronization mechanisms in Golang. We will see all the synchronization mechanisms that Golang have, since wait groups, mutex, select statements, channels, atomics, and so on. So before we start with the video, I want to tell you something. All the code that you will see on this video, you will have it on my GitHub repo, and the link to that repo will be on the description of the video. I invite you to see this GitHub repo where you will find all the code that I am showing you here on this video, because if you have the code close to you, it will be easier for you to understand all the things that I am explaining here. And another thing is that if you like this kind of videos, please hit the like button and subscribe to my channel, because that will help me a lot to grow up on YouTube. So now I will let you with the video. Why we need wait groups? Well, wait groups are here to wait coroutines. So imagine this situation. We are a Golang program and we execute two coroutines to work concurrently. So this coroutine will get the resource A and this other coroutine will get the resource B independently, okay? But our main program, how knows that this coroutine ends or this coroutine ends? Because this main coroutine will have to wait for those coroutines ends. But how this main program knows that? Well, that's where wait groups came. Wait groups will allow to this main coroutine, to this main program, to wait for all the coroutines that this main coroutine execute. So with wait groups, this main coroutine can wait for this resource and this other resource. Well, now we will see this on code. First, I want to tell you that all the code that you can see in this video, you will have it on this GitHub repo. I will let the link on the description of the video so you can check it, and well, I recommend that you have it close to you while you are seeing this video, because it will help you to understand better all the things that I am explaining to you. Well, here we have three functions: do work function with wait groups function and without wait group functions. First, we will focus on these two, without wait groups and do work. So what this function does? Well, this function without wait groups, the only thing that it does is generate 10 coroutines that will do this function, do work. What this function does? Well, this function, the only thing that does is wait 3 seconds and then print the number of this coroutine. For example, the first coroutine will print coroutine number 1, the second coroutine number 2, and so on. And after that, well, this function without wait groups will print. So I will execute this function first without wait groups to see what is happened. So go, and we can see that none of all the coroutines that we execute here are printed on the console. Why is that? Why it seems like none of these coroutines executed? Well, that is because we are not given time to those coroutines to execute, because every coroutine have to wait 3 seconds, and after we execute this 10 coroutines, we finish the program basically, because we just have to print a message and then finish the main function. And when finish the main function, all the coroutines, bye-bye. So we have to here wait for those coroutines that we execute before. So we can here put a time sleep and see what happens. So here we will execute the 10 coroutines and then we will wait for 3 seconds and then we'll execute this message. So I will execute this to see what happened now. And well, we are waiting here 3 seconds and then finish the without wait groups function. But here are printed 3 coroutines. Okay, so 3 coroutines were executed before this final line before this main function ends. If here we wait for 4 seconds instead of 3, we will have to see all the coroutines finished, and then the without wait groups function finish. So we will execute this. We will have to wait for 4 seconds, and then all the coroutines are executed, and then the without wait groups finish message. Why is that? Well, because we have to wait to our coroutines that we executed finish properly. But we can't use this time sleep here to wait for our coroutines, because, well, here we know the duration of each coroutine, that is 3 seconds. But normally we will not know how long will take a coroutine. So we have to make another thing, implement another mechanism to wait for our coroutines, to finish properly. So here comes wait groups. Wait groups are here to wait for our coroutines. So here we declare a wait group variable, and then every time that we are creating a new coroutine, we just have to make this wait group that add function that will increment a counter that is inside of the wait group. And then when we want to wait, before to do that, I want to make sure that all the coroutines that I execute before are finished. So at this point of the code, for example here, I want to wait for those coroutines ends. So here I execute this function, wait group that wait, that is a function associated to this structure. And this function, what it does is wait for this counter that I mentioned before, that we are incremented here, comes to 0. But how this counter comes to 0? Well, here, when I execute this coroutine, I am declaring here a different function that what it does is, when this do work function of this coroutine ends, okay, at the end, we'll execute this wait group that done. This wait group that done, what it does is decrement the counter by 1. So every time that a coroutine finish, we'll execute wait group that done, and with this, we'll decrement the counter by 1. So here, we just have to wait that all the coroutines end to get the counter on 0, and then, well, we just have to print this message safely, because here we already know that all the coroutines takes the time that takes every coroutine will end. So we don't have to be worried about how long takes every coroutine, because with these wait groups, we know that if we go to this line, all the coroutines are done. So I will execute now this function with wait groups to see what happens. So I will execute that and see. Well, we are waiting here the time that we have to wait, and then all the coroutines will be printed because all the coroutines are executed properly. And then when all the coroutines finish it, well, we print this message to end the main function. Well, the first coroutine that executed is the coroutine number 8, the second one, the coroutine number 1, the third one, the coroutine 0. So the first coroutine. And well, here we also see that we don't have the control of our coroutines. When we apply concurrency, we lost the control of our program. So look at this. The coroutine number 8 is the first one on execute in this particular case. If I execute this again, maybe the first coroutine will be another one. Here is the number 9. We lost the control of our program, so we have to apply synchronization mechanism to make our programs work in a way that we want, because maybe we want to execute, I don't know, the coroutine number 7 first. And well, we can apply synchronization mechanism to do that. There are a lot of synchronization mechanisms. This is one of those. Another synchronization mechanism are channels. Channels allows to coroutines to put some message on a channel, and another coroutine will be listen for that channel, and this another coroutine can get the message from the other coroutine. It's a way to communicate two coroutines. Okay, so here in this diagram we can see like this coroutine put a message on this channel of integers because every channel have to have a type, a specific type. Can be an struct, but have to have a type. If there is a channel of integers, we cannot put here strings. And the same for structs. If we have a struct of name, I don't know, dog, we cannot put on the channel of dogs another type of structure like cats. So we have to respect the type of each channel. In this case, it's a channel of integers, so this coroutine will put here a number, an integer, like for example 5, and this other coroutine will be waiting for that message. So if this coroutine comes first and, well, there is no messages here on the channel, this coroutine will wait until this other coroutine puts the message. So this coroutine that is listened to this channel can be blocked by the channel itself, because if there is no message, this coroutine will be blocked and will not execute until get this message from the channel. But if this coroutine puts the message first, well, this other coroutine will get the message immediately and will execute with the other things that this coroutine have to do. So we will see this on code. I remind you, like always, that you will have all the code that you will see on this video, on this GitHub repo, which the link will be on the description of the video. So I recommend you that you have it closer to you while you are seeing this video, because it will help you a lot, okay? So going to the code. Here we have 6 functions: a producer, a consumer, and a with channel function, and another function that emulates the producer and the consumer, but this function is without channels. So first, we will see the without channels function to understand how we will have to implement these methods if we are not using channels. So first, look this function. In this function, we are using wait groups. I tell you that we will use wait groups in every method that we implement with coroutines. When we apply concurrency, we will have to use wait groups. We have here a resource variable. Well, this resource variable, we will pass it to these producer and consumer functions. These functions will execute in the background using coroutines. So this without channel will execute 2 coroutines, one to produce numbers and the other to consume those numbers, like we are seeing this here, but without using channels. So how we will do that? Well, we will do that using this variable here. And well, the producer function, what it does is generates a random integers every 3 seconds. So this is a for loop that never ends, but every 3 seconds generates a random integers, because here we are waiting for 3 seconds. And the same here on the consumer function. We are reading the number of this resource variable that we pass here, the pointer of this resource variable, and then we are waiting 2 seconds instead of 3. And that's because I want to show you that this consumer can print the same message twice, because maybe the resources are not updated by the producer function. In this mechanism, without using channels, maybe this variable or this resource that we have to producer and consumer, well, maybe the consumer consumes twice the same data, and we don't want that. But that are the risks to not use channels in this situation. So I will execute this function without channels to see what happens. Here the consumer reads 0, then the consumer reads 22, the consumer reads 43, 99, 99 again. So here is the example that I mentioned before, where we're using this without channels, a consumer and producer functions using a variable is dangerous, because the consumer can consume the resource, the same resource data twice. So we have to use channels here because it's more simple and more safe. So we will see now the difference between the without channels function and with this other function that is with channels. So here we can see what it does, this function. Well, first, always we will need a wait group like so, and then we create a channel. a channel of integers. To create a channel, we have to use this, and here we have to put the type of the channel. In this case, it's an integer, but can be a string, a float, or any type that you like. Here we are telling to the wait group that we will execute 2 coroutines, and we will have to wait for those coroutines. And well, here is the same of here. We create 2 coroutines to execute a producer and consumer function. But here, instead of writing on the pointer of this variable, here we are writing to a channel, like so. The producer creates a random integer between 0 and 100 and put on the channel, like so. To put things on channels, we have to use these sentences. It's weird, but with time, it becomes normal. And then, well, we just wait for 3 seconds like we do here also. And the consumer, well, the consumer will create a variable n with the value of the channel. So here we are waiting. This consumer function will be blocked if there is no content inside of the channel. Will be blocked until the channel have something. So when the channel have something, some integer, we'll create this new variable n with the value that gets from the channel. So for example, if the producer function produce a number 5 and put that number to this channel, well, this consumer will read that number 5 from the channel and put here on the variable n, and then will print this number. Look that our consumer doesn't have to use a time that sleep to wait for the other number that our producer will provide us. We just have to print, and then we just have to wait here on the channel without using any time sleep. And it's better because maybe we don't know how long it will take to produce a new number on the producer function. So here, well, we just have to print every time that we can get something from this channel where the producer will be putting here new numbers every 3 seconds. It's like you can see here. This is the coroutine producer that will put here numbers on the channel, and this is the coroutine consumer that will consume the numbers that this coroutine producer put here. So this coroutine will get the number and print it, get the number and print it. If there is no number, well, this coroutine will have to wait here to get a new number from this. But this can produce deadlock. That is another problem applying concurrency. But deadlocks and all the problems that generates concurrency and this synchronization mechanism, it's for other section. So now I will execute this with channel function to see what happens. It's the same that we see before, but now the consumer will never consume a number twice. Well, can consume the same number twice, but that is fault of the producer function, because the producer can produce the same number in a row. Well, here we have an example. This example is the same example that you will see on the GitHub repo. Well, to implement select statement, why we have the need to implement a select statement to synchronize coroutines? Well, here in this example, we have 3 channels. First, look this diagram to understand better the situation. We have 3 channels. Our program reads data through these 3 channels. A channel of integers, a channel of floats, and another channel of strings. So our program can read an integer, floats, or a string, and do something with that data. Okay? So if our program receives an integer, well, our program will have to do something. If our program receives a float, okay, our program will have to do something else. And the same logic for the strings, okay? So we have 3 channels, and we have to be listened of these 3 channels. If in this case, we decide to don't use a select statement, we will have to create 3 coroutines specifically to listen every channel. One coroutine to listen the channel of integers, another coroutine to listen the channel of floats, and other coroutine to listen the channel of strings. And every time that a channel gets data from that channel, this channel will have to communicate to the main process and notify that, okay, this main process have to execute something with that data. But like we want to execute while we receive data, we will have to apply another synchronization mechanisms like Mutex or something like that to synchronize. Okay, this came first, I have to do this first, and later, when finished with that task, I have to do the following, and so on. So it's a lot of logic for not implemented a simple select statement in this particular case. So with a select statement, it will look something like this. We have three channels, a channel of integers, the float, and strings. There will be some coroutines that will dedicate to put data through those channels. For example, a coroutine that puts some integers here, another coroutine that puts floats numbers here, and other coroutine that puts strings to this channel. But we will have just one coroutine to listen for all the channels. And the first data that comes from any of those channels, we will handle that and do whatever that we want to do with that data. For example, if I receive an integer, I want to multiply the integer by 2 and then print on the console, for example. And if I receive a float, I want to divide that float number to 5 and then print that number on the console. And if I receive a string, well, I just want to print that string on the console. It's just an example, but there is different functions to execute for every data type that we receive. So here, this coroutine will listen to all of those channels, and the first data that comes to that select statement, because this will be a select statement that will listen for all of those channels, well, we'll execute the logic of that particular data type or that particular channel, because here we are saying that, okay, this channel is for integers, this other channel is for floats, but maybe there are two channels dedicated for integers, but for example, a channel is for ages and other channel is for prices, and both channels contains integers, but those channels have different meaning. So it's the same. The point is that every channel will have a case in the select statement. So if we receive data through that particular channel, the select statement will handle that and will execute the functions associated with that particular data type that we receive, and will handle that in a very easy way. So now we will see this particular case on code. So here we have these three channels: the channel of integers, the channel of floats, and the channel of strings. And well, we have here two functions. One, to execute producers. These producers are three coroutines that will produce integers every 3 seconds, floats every 3 seconds, and strings every 3 seconds. Here are the functions. This will produce a random integer and put that random integer to the channel using these sentences. Here we produce a random float and then put that float to the channel of floats that we receive here as a parameter, and then wait for 3 seconds. And well, the string it's more complex, but we generate a random integer from 0 to 100 and we convert that number to a string, and then we get the bytes of that string, and well, with the bytes we get the hash of that particular string, and we put that hash to the channel of strings. And well, that's all for the producers. The producers are just three coroutines that will never end, because there is a for loop every time in each producer function, but with a wait time of 3 seconds in each one. So that's for the producers. But the consumers, when we execute the consumers, well, here we have the select statement, because this is the consumer here. So the consumer obviously have a for loop, but I will explain that later. But the main important thing is here in the select statement. In every case, we create a variable called data, that this variable will contain the data from a channel. Can be from the channel of integers, can be from the channel of floats, and can be from the channel of strings. So the select statement here is telling us, okay, if I receive for any reason, I've received an integer from this channel, I will put that integer on this variable data and will execute all the functions that have this case. If we have here more than one function, okay, we'll execute more than one function. We'll execute all the functions that we put here. But for this case, we just have one function to execute when we receive an integer. The same for the float. So if for any reasons this channel receive a float, the select statement will create a variable called data and will put here the float that we get from the channel. The same for the string. We'll create a variable called data with the string that we get from the channel. But while we are not getting any data from any of those three channels, the select statement will be blocked until some of these three channels can get some data. So be careful with that, because maybe can produce a deadlock. Because if there is no other coroutines or something that put data to any of those three channels, there is a deadlock, because this will never execute and will be blocked forever. And why we put here a for loop, a for end loop, because this for loop will never end? It's because we want to be listening every time, always, for new data that comes to these three channels. Because the select statement will listen for the first data that comes to these channels. So these channels doesn't have data. This other channel also doesn't have data, and the string channel doesn't have data. Okay, the select statement will be waiting for the first data that comes. And for example, if comes a float, the select statement will execute and will finish. So to be listening again, to be waiting again for some new data, I aggregate this for loop, because every time that the select statement executes, then we'll execute again because of the for loop. And the functions that we use here is just for this particular case to show an example, but can be more complex functions where we receive an integer and we, for example, have to buy something or have to do something more complex than just print the number on the console. But for this purpose of the video, I just decided to print this with this particular signature to identify which function is. In this case, well, print integer, print float, and print the string. So we can identify on the console, okay, there is executing this function because the select statement received that particular string or that particular float or integer. So now I will execute this select function to see what happens on the console. And well, here we have the first data printed by the consumers. The producer of integer produced 52, the producer of strings produced this hash, and the producer of floats produced this float, 27 with 69. We can execute this again to see all the data all the data printed by the consumer, but there's a lot of data. Every 3 seconds will be printed again and again and again, new data. And you can see that not every time we get the same order of consumers executing. And that's because we lost the control of our programs. We cannot decide now when the producer will produce something. That's because we are working with concurrency, with coroutines. But maybe the producer of integers produce an integer and then wait for 3 seconds, and then the producer of floats produce another float, and then instead of execute the producer of strings, it's executed the producer of integers again, and so on. We lost the control of our program. So that's because we have to use synchronization mechanisms when we apply concurrency, not only in Golang, in all the others programming languages. Every time that we work with concurrency, we have to apply synchronization mechanisms to make our programs work properly. Another synchronization mechanism that is very important to us is the mutex. With mutex, we can synchronize the access of multiple coroutines to the same resource, to the same variable. Let's look an example on this diagram. Here we have 2 examples, a without mutex example and a with mutex example. First, we will look this without mutex example. So here we have 2 coroutines that wants to read and write this particular variable that is balance. So these 2 coroutines wants to access to the same resource, to the same variable that is balance. And the coroutine number 1 and the coroutine number 2 wants to do the same, that is read the balance, read the value of this particular variable, and then increment that value by 1. So imagine this situation like you can see here on the timeline, where these 2 coroutines are executed in this particular way, where the coroutine number 1 executes first, and well, this coroutine read the balance of this variable, and at that particular moment the value of this variable was 0, okay, and then well, the operating system quick that coroutine for any reason and put the coroutine number 2 to execute. So the coroutine number 2 at this particular moment reads the value of this balance variable, and well, at that particular moment the value of that variable was 0, and well, then ends and well, increment the value of that particular variable by 1. So at this moment the value of the balance variable is 1, but then the coroutine number 1 executes again, and well, this coroutine only left to increment the variable by 1. So like this coroutine reads at this moment that the balance variable has a value of 0, at this moment this coroutine will want to increment by 1, so will increment from 0 to 1 instead of what we expect, that is from 1 to 2, because at this moment the balance variable has a value of 1. But here the coroutine number 1 doesn't know that. This coroutine only knows that at this moment was 0, so the coroutine number 1 expects that at this particular moment the balance value is 0, 2, like in this moment. But other coroutine changed the value, and the coroutine number 1 doesn't know that. So with Mutex we can synchronize that access to this particular variable. So we can be sure that when we read and write data, we are doing that in a safe way. So here we have this diagram where I try to show you how it will do the same but with Mutex, applying this particular synchronization mechanism that is Mutex. So here we have our two coroutines that wants to read the balance and then increment the value by 1, like we have it here. But here we are applying Mutex, this synchronization mechanism. So our two coroutines will have to ask to this Mutex, can access to that data, can access to that resource. And the Mutex is like a semaphore. We can get a green light or a red light. At the first time, the Mutex will be always on a green light. We can be able to access to this critical zone, that is this. But when a coroutine gets into that particular critical zone, the Mutex will be blocked. It's like the semaphore will put on the red lights. So if this coroutine, the coroutine number 1, access to that resource first, when try to get access to the same resource, it will be blocked because another coroutine is already using that particular resource, and we don't want to multiple coroutines use the same resource at the same time. So this coroutine, if the coroutine number 1 gets first, the coroutine number 2 will be blocked here because this coroutine has the entire access to that particular variable. So this coroutine will have to wait that this coroutine ends to use this particular resource, and when this coroutine finishes to use this particular resource, here this coroutine will unlock the Mutex. It's like we put the semaphore on the green light again, and we continue doing something else but without using this particular resource. And then here the other coroutines, can be more than one, finally can access to this particular resource, because this Mutex at this moment, the Mutex will be on green light again, and this coroutine can access to that particular resource and put the semaphore on the red light, so other coroutines can't access to that particular resource at the same moment. So to understand better this particular situation, we can see here this timeline like we have it here. Well, but with Mutex, always we'll look at this timeline. So here, first, imagine that the coroutine number 1 execute first, because the only thing that can change in this timeline is the order of the coroutines. If here is the coroutine number 1, well, can be the coroutine number 2. If here is the coroutine number 2, well, can be the coroutine number 1. So here, the coroutine number 1 execute first and lock the Mutex. So put the Mutex on the red light for the other coroutines, and read the balance of this particular variable and read 0, because at this moment the value of this variable is 0. Okay, then the operating system quit that coroutine of executing and put the coroutine number 2 to execute. This coroutine try to lock the Mutex, try to get access to this resource, but this coroutine cannot lock the Mutex, cannot get access to that particular resource, because it's already blocked by another coroutine. So this coroutine will be blocked here until the mutex gets unlocked for the coroutine that lock the mutex. So then after that, the coroutine number 1 executes again, and well, like the coroutine number 1 already read the balance of that variable, this coroutine, the only thing that they have to do is increment that value that reads before by 1. So the coroutine number 1 increments the balance by 1, and then finally unlock the mutex. When this coroutine unlock the mutex, well, the coroutine number 2 will access to this particular balance variable and well, will read the balance and will read 1, because at this moment when the coroutine number 1 ends, the balance of this variable will be 1, and well, this coroutine number 2 will increment from 1 to 2, and that's what we want. So now we will see this on code. I remind you that you will have all the code that you will see in this video in this particular GitHub repo. In this repo, I put all the code of all of the synchronization mechanisms that I am sharing with you in my YouTube videos. So I recommend you that you have it close to you while you are seeing my videos, because it will help you to understand better all the things that we are doing on the video. So now we will see this example in code. So here we have 3 functions: a do-work function, a with mutex function, and without mutex function. We want to emulate this particular situation where we have multiple coroutines that wants to access to some variable and increment it by 1. And we want to do that using mutex and not using mutex to see the difference between these 2 implementations. So first, we will look the without mutex implementation. So this function, what it does is, well, creates a variable called balance and initialize that variable on 0. After that, we execute 10 coroutines that these coroutines will do this do-work function. This do-work function receives a pointer to this balance variable and then a flag, with mutex flag that, well, this flag will say to us, to this function, if wants to apply mutex or if not want to apply mutex. So for this particular case, we pass here false to not apply mutex, and well, we here dereference the pointer of this variable and increment it by 1 using this syntax, and then we wait for 1 second in the do work function. So we execute 10 coroutines that do this particular thing. So we expect that the balance variable at the end of this program, it's 10, because we execute 10 coroutines that all of one increment the balance by 1. So we expect that at the end of the program, the balance variable will be 10. But you will see on this code that not every time it's 10. The majority of the time it's 10, but in some situations it's not. And that's for the race conditions that we provoke here when we don't use mutex or any synchronization mechanisms to handle that access of multiple coroutines to the same resource. So because of that, I want to show you that in some cases the variable balance will not be 10, I do this for end loop where I will repeat this process of execute 10 coroutines until I get finally a balance different from 10. And if this function gets a balance different from 10, well, we'll print that balance number on the console. And then we'll execute again. We'll try to find another case where the balance is different from 10, and again and again and again. It's a for end loop. So we will execute this. So here we have to wait until, well, here we have two examples now of that we are executing this function, but we are getting a balance difference from 10. In these 2 cases, we got 9 instead of 10, and that's for the race conditions. Here we have now 5 cases, 6 cases of race conditions in this particular execution of without mutex. So you can see that if we don't apply synchronization mechanisms in some cases where when we apply concurrency, it's dangerous, because if we execute this function once, maybe we get 10 as a result, and maybe we think it's okay, but it's not okay, because in some cases will not produce the same value, the same results, and it's dangerous. It's totally dangerous. So now we will see the implementation of this using Mutex, and then we'll execute the function with Mutex to see the difference between these two implementations. So the function with Mutex, it's the same that this function, but here, well, we just execute this once. We don't execute this forever, because forever will be the same results. The balance always will produce the balance tens, because always will produce the same results. The balance variable will have the value of 10. It will never get some different value of 10, because we are applying Mutex. With Mutex, we guarantee that. So here, well, we execute 10 coroutines using the same logic here, and the only difference is that here we pass the flag on true. So here in the do work function, we'll execute this part of the if statement, and here we'll apply Mutex. So it's like we see before on the diagram. When a coroutine get access to the Mutex, okay, we'll ask to the Mutex, can access to the resource, or I have to wait? If there is no coroutine using that particular resource, the Mutex will respond to the coroutine, no problem, came and use the resources, because none of those coroutines are using the same resource that you want to use, so came and use it. But if there is already a coroutine using the resource that we want to use, the Mutex will say to us, wait here until the other coroutines that are using this resource ends. Okay, I wait. So here, with this sentence, we ask to the Mutex, can I access to the Mutex? If the Mutex is already used by other coroutine, will be blocked here. But if it's not, if any coroutine are using this particular resource, we will be able to access to that particular resource, and well, for this moment, all the other coroutines will not be able to access to this particular resource, to this particular critical zone, because we already are inside of this critical zone. So the other coroutines will be waiting here until our coroutine that gets this resource, that lock this Mutex, doing the following, that is unlock the Mutex. When we unlock the Mutex, we'll put the Mutex on the green light again, so other coroutines can be able to access to this particular resource. And that's all, because with this we are guaranteed that all the coroutines that wants to get access to this particular resource in a safe way. So now I will execute this function with Mutex to show you that always we will get a result of 10. So I will execute this, and well, we get it here 10. I will execute this again, and well, we get 10 again. I will execute again to see what happens, but it will show me again 10, because always we will have the same results when we apply synchronization mechanisms like Mutex to this particular resource that all the coroutines want to access at the same time. So when we have to apply Mutex, well, we have to apply Mutex when we know that multiple coroutines will want to access to the same particular resource. If multiple coroutines want to access to the same particular resource in any time, it doesn't have to be at the same time or to do the same, because maybe we have another coroutine that do another work, another things with this variable of balance, but it's the same. If more than one coroutine get access to the same resource, we have to apply Mutex. We have to, because if we don't apply Mutex or some synchronization mechanism that allow us to be sure that when a coroutine get access to this particular resource, this resource will be safe from that moment until the moment that this coroutine ends or ends to use this particular resource. We have to be sure that, because if we don't be sure of that, we will not be sure about our programs, because our programs can produce race conditions or some other concurrency issues. So we have to be sure about that to don't provoke any of those concurrency issues. Other synchronization mechanism that we will see is the atomic. Well, this will be the last synchronization mechanism that we will see. Atomic is very similar to Mutex. With atomic, we guarantee that only one coroutine can access to some resource. It's very similar to Mutex. Here in this diagram is show you how works Mutex, but for this case it's almost the same, because with atomic we guarantee that this resource, this balance variable, get access by only one coroutine, only one concurrent process at the same time. So if one coroutine, one concurrent process are using this variable or this resource, all the other coroutines will cannot access to that particular resource. So at the end is the same that Mutex, but with different sentences to declare this synchronization mechanism. So like it's almost the same as Mutex. Well, with Mutex we want to prevent race conditions in our program. So with atomic it's the same. We use atomic to prevent race conditions in our program. So I will explain you the same case that I explained you on the Mutex, but I have to explain this again for those who don't see the Mutex section. So where here we just have two coroutines that are working concurrently. These two coroutines want to do the same, that is read the balance variable and then increment it by 1. But these two coroutines are executing without a synchronization mechanism. In this case, Mutex or atomic. So these two coroutines doesn't have any synchronization mechanism to access to this particular variable. So here on the timeline, we can see that maybe our coroutines execute in this order. And if execute in this order without a synchronization mechanism, we have here a race conditions. Because here our coroutine number 1 reads the balance of this variable. Because here our coroutine number 1 reads the value of this variable and gets 0, because at this time it's 0. Then this coroutine quick and get into execute the coroutine number 2. The coroutine number 2 also read the value of this variable, and like at this time it's 0, read 0 too. And well, this coroutine doesn't quick, so this coroutine ends and well increment the value of this variable by 1. And after that, the coroutine number 1 goes back to execute. And well, this coroutine already reads the value of this variable. So this coroutine already know that this variable has a value of 0. And then, well, this coroutine will end incremented this value by 1. So we'll increment from 0 to 1 instead of what we expect, that is going from 1 to 2, because at this moment this variable has a value of 1. But this coroutine, like this coroutine reads here the value of this variable, this coroutine doesn't know that in the middle another coroutine increment the value or do something with the value of this variable. So to prevent that, we have to use a synchronization mechanism. We can use Mutex or, in this case, atomic. I will show you an example of how to use atomic in code. So here I have, like always, 3 functions: a do work function, a with atomic function, and another function that is without atomic. I want to show you the difference between using atomic and when we don't use atomic, and well, when we don't use Mutex2 or any synchronization mechanism. I want to show you the difference between using synchronization mechanism properly and when we not use synchronization mechanism, what happens in the cases where we working with concurrency, because all of this will never happen if we work in a sequential way. All of this happens when we try to execute multiple coroutines, multiple processes in a concurrent way. So first, I will show you this without atomic function, what it does. Well, this is a for and loop, so we'll execute every time. And well, here we'll execute 10 coroutines, and these 10 coroutines will try to increment the value of this balance, that initially it's 0, by 1. So at the end, this variable must have a value of 10. But what happens when we don't use a synchronization mechanism like Mutex, or in this case atomic? Well, in some cases, the value of this variable will not be 10, will be different from 10. And that's because the race conditions that we provoke here. So first I will show you this so you can see that I am telling you the truth, that in some cases this balance will not be 10. And well, I forget to show you this do work function. Well, this do work function will receive a pointer of this balance and this flag that is with atomic, that is a Boolean variable that, well, will help me to decide in this function if I use atomic or if I not use atomic. So if in this case without atomic, I just pass here false. So in this case execute this code, and well, this code doesn't use synchronization mechanism. It's just trying to get into that particular variable and increment the value from there. Like we can see here, we doesn't have any synchronization mechanism. The coroutines are trying to execute directly from the resource, and that is dangerous because can produce race conditions, and it's what we want to see here. Well, if we pass here true, well, we'll execute this part of the code, that is the atomic part, where we apply this synchronization mechanism, but I will explain that later, once we see first this with atomic function in action. So here I will execute this without atomic function to see what happens. So this function will execute every time looking for, in like this case, a balance different from 10. The majority of the time we'll find a balance of 10, but that is the dangerous thing here, because race conditions are not always telling us you have an error here. No, it's in some cases depending on how these coroutines are executed. So here I am getting a lot of values different from 10, and that's because this without atomic function is executing in a for-end loop. It's executing every time looking for new balance difference from 10. But well, I have to shut down this function because it will execute forever if I don't shut down this function. So I will shut down this function, and then I will show you the difference between this without atomic function and this with atomic function. Well, here with this atomic function, it's almost the same that we have here, but without the for-end loop, and that's because here always we will get the same results because we are applying synchronization mechanisms, in this case atomic. So it's the same. This function executes 10 coroutines, and these 10 coroutines will try to increment this variable of balance by 1. So at the end, the variable of balance will have a value of 10, but in this function always will have a value of 10, and that's because we are using synchronization mechanism. In this case we are using atomic. So atomic is a package that we import here so we can use it, and here we have a lot of functions like this: add integer of 64 bits, add integer of 32 bits, compare and swap integers of 32 bits, compare and swap integers of 64 bits. And well, we have here a lot of functions that we can use from this package of atomic. All of those functions of this package of atomic will guarantee us that we are executing this in a safe way. But for me, Facundo, I prefer to use Mutex instead of this atomic, because with Mutex I feel like I have the entire control of when a coroutine can access to some critical zone and when not. But that's what I feel. Some people maybe like to use atomic instead of Mutex, but I like to use Mutex instead of atomic. And well, I just have to show you how this with atomic function works, but it will show you a balance of 10 in every execution. So, well, I will execute this function to see what happens, and well, here we have a balance of 10, waiting 1 second. I will execute this again, and well, I get here 10 again. I will execute again to show you that I will get 10 again, and of course I get 10. And that's because we are applying synchronization mechanism, because we are applying here atomic. And well, that's all for this video. I hope that you could understand all and enjoyed the video, because that is important too, that you enjoy the video while you are understanding and learning new things, like in this case synchronization mechanisms on Golang. And well, if you like this kind of videos, I will ask you again that please, it's just 2 buttons, the like button and the subscribe button. Hit it. With that, you are helping me a lot. So please, hit the like button and subscribe to my channel, please. Now, I will say goodbye to you. See you on the next video.